Okay, precalc chapter 3.1. This is exponential functions. We talked about parent, family, child, and parent graphs back in chapter 1.5. So this is more of a recap of what a exponential function looks like, because we introduced at that point quadratics, exponentials, square roots, cubed roots, cubic graphs, all these different types of graphs. Remember, exponential growth graphs, though, are all based off of this. Y equals b to the x. An exponential growth, or graph, come in two varieties. You got growth and you have decay. Growth, guys, is when b is bigger than 1. Your base. The number, the letter that, that you're making your exponent on. If I have something just slightly bigger than 1 and raise it to a power, any power, the number will result in a larger number. On the flip side, if the number is between 0 and 1, and I raise it to a power, so anything a little bit less than 1, if I raise it to a power, it will start to get smaller and smaller and smaller. Growth and decay have very large implications on populations, radioactive material, money. And we all like money. Money can be exponentially grown if I invest it into a savings account, small, or invest it in the market. It can decay if I'm paying a mortgage or a car loan. I still got to pay interest. So we're going to be able to get interest off of things, make payments, which lowers our interest every time. And what I want to talk about first is that parent, that y equals b to the x. We've done this before. This is what we call a parent. I stripped away all of the moving parts. And we got growth and we got decay. Now here's the cool thing about exponential functions. They have things in common. They all have a y-intercept. And if you think about y-intercepts all have a 0 in the x, right? And so if I put 0 in for x there, anything to the 0 power is 1. Hence, I have a y-intercept at 0, 1. We also, hopefully, remember that all of these have an asymptote. You can't start with nothing and end up with something, and you can't start with something and lose everything by taking a power. It doesn't work that way. And so y equals 0 is that horizontal asymptote. The only difference between the two graphs is obviously the direction that it moves, but the other part is I need one more piece of information to make a really good graph. And so what that is that I need to find an extra point. Because, this is why. Exponential growth graphs, guys, start low, end up high. Decay starts high, ends up low. Right? We've done this before. I'm okay with understanding this side, the left side of a growth, because it's going to approach that asymptote, which is at 0. I understand over here that as it decays, it will approach 0 but never be there. So that is okay. But what's it doing on this side? What's it doing on a growth right side? Is it gradually flowing? Or is it supposed to take a sharp turn like this one actually has? I don't know. I call these the tails. And so if I want to know what the tail is doing, I just kind of find a point on that side. And so I choose a point that's close, 1 for a growth, -1 for decay. So I want to basically anchor that tail, because the tail will pass through that point and I'll know a little bit better idea. Now, why do I choose to stay close to home? Because think of this. What happens if that base was like an 8? 8 to the first power is 8. 8 squared, 8 to the third power Oh, it's bigger than that. It's 8 times 8 times 8. 8 to the 4th power, 8 times 8 times 8 times 8. It gets very large very quickly. Yes? So therefore, I would have to be able to graph that number. I can graph something like a 1/8 or a 1/12. But to graph 12 to the 5th power, ooh, I don't have a big enough graph for that. My paper's not big enough. I'd have to scale it. I wouldn't be able to see the rest of it. So choose something close. 1 is a very good option. Okay? Now, of course, this is the parents, or this is what a parent looks like. So we don't always see or have a parent. Now, I have 2 things on here. Let's do actually just the bottom half first. I want you to graph just a parent. I want you guys to get this idea before we move up and talk about the child stuff. I want you to graph that parent. There's only 3 things I need. Most of the other times, I say most, a lot of the other times though, when we did this whole parent, family, child, and we found a parent, didn't we use the Fab 5? -2, -1, 0, 1, 2? I'm not using the Fab 5 here. I'm just using those 3 pieces of information. A y-intercept, an asymptote, and an extra point. So, this right here is an exponential what? Growth. It's a growth because 3 is not a positive because it's bigger than 1. So if it's bigger than 1, I got a growth. Okay, but guess what? That does not affect the fact that my y-intercept is where? 0, 1. I have an asymptote where? Y equal 0. But that does have implication that I have an extra point. Where would my extra point be? What side do I want to choose this on? It's growth. Choose it on the tail. The tail will be on what side? The right side. So I put in something like 1. And if I put 1 in for x, it'd be 3 to the 1st power, and 3 to the 1st power is 3. Graph it. Graph those 3 things, and you'll have a beautiful looking graph. Y equals 0 is a horizontal line. 0, 1, and 1, 2, 3. So 1, 3. And if I connect them, there's my exponential graph. Boom, I'm done. If I asked you to graph those, you guys would be happy graphing those all day, correct? But of course, this parent is eventually going to be stretched, shrunk, horizontally, vertically, moved left, right, up, or down. So, to move this and change this graph, I'm going to use the parent, family, child. Parent, family, child brings back all of the extra things. Now, I had to make a slight modification on this one. Normally, the letter in front of x is a b, but it's usually lowercase. I don't want you guys getting that mixed up with the fact that the base is a b. So I use a big B. Okay? Big B. Big B is your horizontal stretching and shrinking. A is your vertical stretch or shrink. And it also talks about the reflection about the x-axis. Remember, if it's negative, it flips and turns upside down, right? That's reflected about the x-axis. But look what I put with B. B was your horizontal shrink or stretch, but I say opposite in here. Why? Because anything to do with x always seems to do the opposite. And it's reflected about the y-axis, so that means it goes this way. It flips it around the other way. It goes backwards. H is your translated left, right. Oh, I forgot to do something there. That's with x again, so therefore I should put Opposite, because it always does the opposite of what the formula says. K is your translated up and down. So that affects your y's, right? So our job is to run through this again. How to do the parent, family, child. You guys ready for this? Hold on to your hats. Here we go. I want you guys to graph that using the parent, family, child method. I've got 3 times 1/2 to the x plus 1 minus 2. It's an exponential graph. So if I wanted to, okay, this is a child. If you're having a problem with a child, you go find its parent. And what would the parent graph here be? Y equals 1/2 to the x. Now you think to yourself, what a wonderful world. But anyways, you would say, hey, is this growth or decay? It's not growth, it's decay, because 1/2 is less than 1. So if you need to, put decay next to that so you don't forget it. But, guess what? I still have a y-intercept at... All parents have y-intercepts where? 0, 1. It has an asymptote where? Y equal 0. Get used to the idea of saying y equals 0, guys. And it has an extra point. Now, that's why we stated it was decay, because I'm going to choose what? -1. What happens when I use negative exponents? What can it do to fractions? What do negative exponents do? When I plug in a -1 in for x, what's it going to do to that 1/2? It's going to flip it. It becomes a 2. The whole reason of making some nice numbers, that's what I'm trying to do. That is my parent. It's done. Why do we use the parent, family, child? I use the parent, family, child because it gives me a system and a place where I'm allowed to both describe what's happening to the graph and 2, have a methodical way using order of operations to graph a complicated function. If I am done talking to the parent, I now can move to the family. The family brings back A and big B in this case. You only have an A, and A happens to be 3. What would that 3 do to my graph? Vertical stretch of 3. Hey, is it supposed to reflect it? Is it negative? It's not negative. So therefore, if I don't have to do it, do I have to talk about it? No. Okay? So don't talk about it. But what does it mean when I vertically stretch something? It gets bigger in which direction? X or Y? The Y's. So, do I have to change any of my X's? No. So 0 still stays 0. -1 still stays -1 because I'm moving in the Y direction. And if I'm stretching it 3 times taller in the Y, I'm going to multiply all the Y's by 3. And 1 times 3? 0 times 3? And 2 times 3? 6. You're always applying it to the points from the parent. When we move to the child, we will not multiply, we're add or subtract to the family. You're never trying to build it from scratch. You're always using the stuff that you already have. You're just applying. You're adding the new parts. Remember the assembly line. Once we're done talking to the family, we move on to the child. The child is the whole thing. And what are the words? What are we doing to this graph? Translated, where's it going? Left?
Right. Left.
How far? 1. Remember, if it's with x, it's going to go left or right. And this one, because it's with x, always does the opposite. So it says +1. Nope, I'm actually going -1.
Okay.
This is my k value, -2. That does exactly what it says. If I'm going to go -2, I'm going down 2. Guys, make sure you're writing translated down 2 or 2 down. It doesn't matter which way you want to say that. Now, if I go left 1, what am I doing? I'm affecting my x's by taking all of my x's and subtracting 1. If I'm going down 2,
You're going down and you're subtracting.
I'm subtracting 2 from my y's. Notice the same 3 pieces of information will be there. So, if I start at 0 and I have to go left 1, I am now at -1. If I start at 3 and I go down 2, I'm at 1. If I start at 0 and I have to go down 2, did it moving it left do anything? It's a horizontal line. I can move a horizontal line left and right as far as I want, and it's not going to change. Start at -1 and I go back 1. Ooh, I'm at -2. 6 turns to a 4. You just have to graph these 3 pieces of information, and you have now just graphed a complicated looking exponential function. We'll start with the asymptote. Y equals -2. There it is. Then I could plot -1, 1. -2, 4. And we know the graph will fall because it decays, and it decays to the horizontal asymptote. Look at that. Pretty cool, huh? That's graphing an exponential function using PFC. Now, word of advice. This is not our first rodeo with the PFC. Last time, I was maybe a little bit more forgiving that people forgot to write things, forgot to state things. All of this needs to be there because that demonstrates that you, number 1, can describe how you're attaining that graph. And then 2, you're showing the flow of order of operations. Notice, I multiplied first with the multiplied by 3, and then added, subtracted second. That's a good way to tell which one comes first. Order of operations. Multiply, then add. So let's move on to compound interest. Let's make some money. Compound interest, guys, is how basically most accounts work for savings, how things work on investments, be able to figure out how much money you're going to have at the end. A is the amount at the end of the investment. P is your principal, the amount of money going in. R is the rate. So we usually say, hey, 5%, 6%. But to use it, it has to be a decimal. And T is your time. And I see I left one off. What's the one I left off? N. N equals number of times interest is compounded. The number of times your interest is compounded. So A equals P times the quantity, 1 plus R over N, and that to the N times T power. Now, A lot of this is pretty interesting. You guys probably can understand what those mean. But N, compounded interest. Number of times interest is compounded. If interest is compounded yearly, then N is, how many times is yearly?
1.
1. If it's compounded monthly,
It's 12.
N is 12. Semi-annually,
Would be
twice. Daily, 365. Okay? So N is what's going to change, or can change. Compounded interest, guys, is like the number of times your bank or whatever person's looking and giving you the money is going to look at your account in a year. The more times we're going to find that they check and give you interest, the more money you're going to make. Because the more interest times they check, they give you a little bit of money. And they check again, they're giving you more money on the more money, which then leads to more money. So, let's put this into account. That's a little small on the screen up there, but I'll read it. It says, if you give $1,000, you're going to invest $1,000. We're all walking to a bank right now with $1,000 in our hand. Your savings, you're going to save this at 8% per year. How much will be in the account at the end of 10 years if no other deposits or withdrawals are made, and the interest is compounded 3 different ways? I want you to compound this semi-annually, quarterly, and then daily. And we're going to find, hopefully, the more times you do this, the more money you'll have. So we have $1,000, 8%, which is a pretty good rate, for 10 years. So it's a good chunk of time. But what you guys need to realize is that you're not going to touch this money. That's the powerful thing about this. So, if I'm doing semi-annually, we'll do this first. How many times was that again?
Is twice.
Twice. Quarterly?
Is 4 times.
And daily?
365.
Okay. So we have to check this money 3 different times under 3 different investments. We're all going to use the same equation. I got $1,000. 1 plus, what was the rate again?
0.00.
It's 0.08 because I have to put it as a decimal. Over, N the first time is 2. And 2 times 10. 2 times 10, look at this, guys. I'm going to break my rate up to smaller pieces, but over 10 years, the interest is going to be checked 20 times. It's happening more often, right? If I check something twice a year for 10 years, it's 20 times. Now, how do I do this? Well, first of all, you're going to have to use a calculator. I say you do the inside stuff first. Take 0.08, divide it by 2, enter. Plus 1, enter. And take that to the power of, we know 2 times 10, that's 20. Take it to the 20th power. Enter. Multiply that by 1,000. How much money am I going to have, or are we going to have, after 10 years of doing absolutely nothing? I'm assuming it's around $2,000. 2,191 and how much change? 12 cents, give or take. Look at that, guys. I more than doubled my money doing absolutely nothing. Wouldn't you guys like to have that kind of money? What if I went to the second account? What if I said, hey, if I had an option, let's go with quarterly. If I went to quarterly, I'd still put my $1,000 in. My 0.08 rate would now be cut into, what's N? 4 times. And I have to do 4 times 10, which is 40. So now it's going to be checked 4 times a year for a total of 40 times over those 10 years. So take 0.08, divided by 4, add 1, make sure you enter all these things, and then take it to the 40th power. Multiply by 1,000. Still $2,000, but I'm guessing it's 2,208. Look at this. 208, what's the change? Do we have 0.4. So essentially, $17 more for them, for the bank to check it 2 extra times a year. Which account are you guys going to use, guys? I'm using quarterly right now, aren't you? Check it one more time. This time, every day, your bank's going to check it for you. Every day, they're going to look in there, give you a little bit of interest. But the next day, they're going to give you an interest on that interest. The next day is the interest on the interest on the interest. Plus your original principal, right? So, it's going to get bigger. 1 plus 0.08 out of, wait, how many times we checking this? 365. And that's 365 times 10. I think we could pretty much do that in our head too. That's 3,650 times they're going to check it over the 10 years. That's a lot of times, isn't it? I think I'm still going to have $2,200, but how much? 25. 0.35. An extra $17 again. From checking it twice a year to checking it daily, I've gained over $30. Doing nothing different than actually just choosing them to look at it more often. This works the opposite way. I'm pretty sure at some point, every single one of you is going to buy a car, buy a house, and make payments. The more times you make payments, the more times they're going to calculate how much you still owe them. So if you make monthly payments, they're going to check it once a month, 12 times. If you make bi-weekly, so twice a month, you can actually shave off several months off your loan just by making the same payments, just cut in two. So know that fact. Wait a minute, guys. I'm assuming most of us in here have a job, or at some point we could probably scrounge up $1,000 over a year by doing some odds and ends around the house. What if you guys took this $1,000 daily? Well, hold off on that thought right now. Let's do this. What if we said, I don't want to check it daily? What if I said, I want them always looking at my account? Then we'd have to use this one. Guys, don't rewrite this part. Don't write this part. This is the same exact problem. I just said at the end, put compounding continuously. This is continuous compound interest. They use PERT. A equals, that should be A equals, sorry, I have a Y there. I want A equals, take that out of there. A equals P R E to the RT. That's an E. E on your calculator. When I use E, it's continuously being looked at. So, it's not going to be a huge improvement over daily. But, if I said I want to look at this continuously, I could take the same $1,000, is what this problem is asking me to do here. E to the same rate, 8%, over that same 10 years, how much money am I going to have? Now guys, make sure you use parentheses here. If you're using the old standard gray box calculator, you're going to have to do 0.08 times 10 first, and then second E to raise it as a power. But it's still 22,000, or 2,200, sorry. Wow, 22,000. Not yet. What's that? His second natural log. If you're on a graphing calculator, it's underneath your natural log button. How much money am I going to have? E to the power of 0.8 is what it comes down to. It's going to be 2,200, still 25, point though, 54 is it? So from daily to continuous, it's really only like a 40 cents difference. But that 40 cents can make a huge difference if I extend my time. So this is what most banks use or investment starts to use, is the continuous thing. So there's a way to do this continuously. So now let's talk about this situation. What if, guys, we took this $1,000, we invested it with an 8%, which is a good rate, and I left it there until you guys wanted to retire. Let's just say 40 years from now you're going to retire. So what if I left that $1,000 sit for a continuous rate of 8% for 40 years? Because in 40 years we'll be close to age 60, right? Now you guys probably won't be able to retire until you're 80. But that's the way that things are going in this country, right? But how much money are you going to have in 40 years? Off of $1,000, not touching it. Someone's got to have an answer by now. 24,000 and change. $24,000 by just putting $1,000 in a bank right now and not touching it. Wait a minute, guys. What would happen if you put $10,000 in? You would multiply by 10,000, which means it'd be 245,000. $250,000 if you could invest $10,000 right now. The power of money, power of investing. Now, 8% is a pretty good return. Now, I'm assuming most of your parents have a 401k. Most of you guys will also have one of these types of things. It's your investment type thing. But think of this, guys. Your parents, when your parents started working someplace, started doing these things, they didn't just put it, hey, I'm going to put $1,000 in and walk away. They put the money in, and they keep putting money in. So that $1,000 is growing every year and earning interest on that. So this $24,000 would start to grow even more and more and more. The idea here is to invest young. It's harder to invest when you're younger because you're trying to start off, you got life, but it can pay off the biggest. A matter of 5 to 10 years of investing makes a huge difference. Homework, guys. 2 different things. 21 and 31 deal with the interest stuff. And then I want you to both describe and then graph using the PFC these 2 graphs. Okay? Have a great day.